Hello, good evening to all. Good evening and welcome to the tutorial session for the course Dynamical System and Control. And I hope you all are able to see my screen. Anybody please confirm if my screen is visible.
Yes, ma'am.
Okay,
Yes, ma'am. The screen is visible.
thank you so much. Okay, before starting the tutorial session, have you all gone through the video lectures that have been uploaded? So for week 1 there are 5 lectures. Have you all gone through those video lectures? Okay, so I assume that uh, you all have seen those video lectures. So in this course, so let me give you a brief recap of what week 1 has covered. So in the week 1, it started with the motivation for studying differential equations or the dynamical systems. So we all know that dynamical systems are basically those systems that varies with time or that progresses with time. So we model those systems using differential equations. So now there are two types of differential equations that can be ordinary differential equation and partial differential equation. So we will start with the ordinary differential equation first, and it was explained that there are various practical systems. For example, various motivating examples have been covered in the lectures, starting from pendulum system, the atomic waste disposal, or the population growth systems, and it has been shown that all these systems can be modeled using ordinary differential equations. All right, so that is the motivation for studying ordinary differential equation, or we say ODEs, because most of the practical systems that we have can be modeled using differential equations or ordinary differential equations. Okay. Now, once we have modeled our system using ODEs, the first question is how we can see the solution of these ODEs. Okay, now with that question in mind, the natural doubt is that whether that ODE is solvable or not, or whether the solution will be unique or not for a particular initial condition or on a particular set, right? So for that there is existence and uniqueness theorem that have been stated and proved in the lecture series. Whether it has been said that the ordinary differential equation or an initial value problem, suppose we have an ordinary differential equation of the form y dot equals to f of t comma y, and we have some initial condition yt naught equals to y naught, then what will be the condition on this function f such that the solution y of t will exist and it will be unique? Can anyone tell me the condition? So the condition for existence of solution is that this f should be continuous. Okay, so if the right hand side of the ODE is continuous, then we are sure that the solution will exist. But that doesn't give us the guarantee that the solution will be unique. Okay, so what is the extra condition that should be satisfied such that the solution will be unique? What property the F should have to have a unique solution? Anyone
Ma'am,
remembers
Lipschitz,
that?
it satisfies the Lipschitz condition, ma'am.
Yes, the uniqueness comes from the Lipschitz condition. Okay. Okay, so this was the core of the this was the core topic for, I think, lecture 1, 2, and 3. So in those three lectures, uh, uh, we studied how the solution of an ODE can be made unique. Okay, so the one property that we should learn is that how to identify whether the right hand side of this ODE or this F is Lipschitz or not. Okay, so we will go through some problems where we will identify whether the this function is Lipschitz or not. And after that, what we have covered, uh, also we have seen when we can say the right hand side is linear or non-linear. Okay, so again we can uh, divide the ODEs as linear and non-linear one. Okay, so what property should this function should satisfy to have a linear ODE? It should be linear with respect to the dependent variable or the independent variable.
The dependent variable, ma'am.
Yes, it should be linear with respect to the dependent variables. So suppose we have function differential equation of the form, sorry, f of x comma y, then this f should be linear with respect to y. Okay, because here y is the dependent variable. And if it is not linear, then the system will be non-linear. We will also have some problems whether we will see how we can identify whether the system is linear or non-linear using the linear operator theory. And what else we have covered? So in the last part of the lecture, we started with the linear ODEs and how we can represent a differential equation using a set of first order differential equation. Okay, and then we saw how to represent the solution of those first order equations and to identify whether it is an autonomous system or a non-autonomous system, whether it is homogeneous equation or non-homogeneous equation. So these were all the topics that have been covered in week 1 of the course. Okay, so now let's start with some problems based on these topics. Okay, before starting this tutorial session, I request if everyone can introduce themselves, because that would give me an idea of what we can cover in this tutorial sessions. Uh, whether you want me to have the explanation or a kind of revision of whatever have been covered in the previous week, or you want me to solve questions based on the topics, or we can have something like we solve the problem and verify that in MATLAB. So I can decide based on what um, qualifications or from which field people have joined this course. So I want you to introduce yourself and a brief uh, from what you are studying and from where you are. Okay, so can we start? Anyone can please start.
Oh, yes, good evening all. Good evening, ma'am. I'm Dr. Subhrojit Roy. I'm an assistant professor in Hirmo Chandra College in Kolkata. So I am in, my subject is mathematics. So I think it will be good if you kindly revise all the topics for the previous weeks and give some demonstration on MATLAB also. So it will be helpful for me, I think, other. Thank you.
Okay, thank you. And so we have Pawar Pritesh.
Yes, madam.
So can you kindly give your introduction, what you are studying or where you are right now, uh, means what you are doing and why you have joined this course?
Yes, madam. Yes, madam. Hello.
Yes, yes, hello.
Yes. Actually, I am a assistant professor in Gujarat and part-time PhD student in NIT Bhopal.
Okay,
So I am doing a coursework for this course. That's it.
okay, okay, thank you. So next is Navneet.
Yes, ma'am. Good evening, ma'am. Good evening to all. I'm Navneet Rana, Assistant Professor in Mathematics in Punjab, and along with it, I'm a research scholar in mathematical biology, in which I am basically doing the research on dynamical system of population growth model. So I think this course is very beneficial for me.
Okay, okay, thank you. Surendran.
Yes, ma'am. I'm audible. Hello.
Yes, you are audible.
Yes, ma'am. Good evening. So my name is Surendra. I'm doing my MTech at Indian Institute of Space Science and Technology. My MTech specialization is in aerodynamics and flight mechanics. I chose this course because I wanted to do my research project on flight dynamics and control.
Okay, thank you. Then we have Prabhu.
Good evening, ma'am, and good evening to all. Am I audible?
Yes, yes.
Myself, Prabhu, ma'am. I'm a research scholar from NIT Trichy. Yeah, I'm right now. I'm studying subjects related to controls because my PhD is oriented towards autonomous guidance kind of topics. So I felt this will be useful. And basically, I'm an aerospace background person. So I
Okay,
think a review or focus about what was covered in that recorded sessions would be better for me. I just want more understanding. That's it,
okay,
ma'am.
okay. Kasturi. You are not audible, Kasturi. Sorry, I couldn't hear you, Kasturi. Okay, so anyone left? Okay, so the most of you are either PhD scholar or assistant professor. Okay, so I forgot to introduce myself also. So My name is Iram Taslima and I am a Prime Minister Research Fellow at the Department of Electrical Engineering, IIT BHU. And I'm pursuing my PhD basically in the field of quantum control. And I'm also the TA for this course.
Hello, ma'am.
Yeah, hello, Kasturi.
Ma'am, this is Sai Chandra. I'm studying my MTech in Anurag University,
Okay,
and this is a credit-based course from our college.
okay, okay. Thank you.
Okay, ma'am.
Okay, thank you everyone, and once again I welcome you all. Okay, now so for this week I've prepared few questions that we will go through, and in the next week I will try to have a brief or a thorough recap of those recorded lectures and simultaneous question solving, and if time permits we will have tutorial sessions also based on the question that we will solve. So basically all these are ODEs, and after finding solutions analytically we can also visualize those solutions using MATLAB. Okay, so that would also help you in your research if you are solving some ODEs and want to simulate it and want to see how those trajectories will evolve as t goes to infinity, or how it will change if we change some parameters, because by mathematically we cannot solve every equation by changing every parameter. That is very clumsy task. So in MATLAB we can visualize all those things very beautifully. So I will try to formulate 1 to 2 problems every week and have a MATLAB demonstration of the same. So will that be okay for everyone?
Yes, ma'am.
Yes,
Okay,
ma'am.
Yes,
okay,
ma'am, that would be helpful.
okay. Thank you then. So for this week, let's try to solve some problems. And in the next week onwards, we will do as suggested. Okay. Okay, so we'll start with an ordinary differential equation where we are given, let's say, dy by dx equals to 2y, or just a minute. Yeah. So we have dy by dx equals to minus 5y minus 2y square, where it is given that y of 0 equals to 1. You have to find out the limit as t goes to infinity for the solution. Sorry, the argument is x. The limit as x goes to infinity for the solution y of x. So I request all of you to please give it a try. Then I will show you how we can solve this. Uh, First, let me know whether this system is linear or non-linear.
Non-linear, ma'am.
Yes, this is very clearly, we can see that we have the term y square. So this is the dependent variable, and we have non-linearity with the dependent variable. So this system of equation is non-linear one. If you have gone through the recorded lectures, you can identify that this type of ODE resemble some type of ODE that have been discussed, or it resembles some model. Can anyone identify? And that model uh, has been studied in very detail in those recorded lectures. So if you remember the population growth model, so how we have modeled the population growth model? It was like dy by dt equals to ay. If we have a linear growth or an exponential growth, we have modeled it like dy by dt equals to ay. Okay, and then we modified that model by assuming that there is some competition. So, because of that, the population doesn't grow linearly, and we have some competition uh, because of which the population doesn't grow linearly, and we model that term using by square. So thus this model resembles the one that we are given. Yes, this is exactly the model of the population growth, where the coefficients are a equals to -5 and b equals to -2. Now, what was the solution of the population growth model? So let's derive its solution. And in order to find the solution for this general ODE, because if we can find out the solution of this ODE, we can easily find out this limit by putting the value of a and b, which is given over here as -5 and -2. Okay, so let's generalize the solution of population growth model. What is the general solution for this population growth model? Okay, where y denotes the population at time t. So we have to do nothing. We can just separate the variables because it is in variable separable form. We can directly write dy by by square integral. So we'll start from y naught to y. So since we are integrating to y, let's change this variable as some ds. Okay, and the right hand side will be so we will integrate it to, so this will be nothing but t minus t naught we can write. Now how we can integrate this part? So let me write it again. It is y naught to y ds divided by as minus bs square. So this is a type of these type of integrals we have solved in our class 12. What we can do, we can separate it using fractions. If we do so, we can write it as 1 by a, this is b by a minus bs Can we write it like this? Because if we solve it, we will get ds by as minus base square. Okay. Now what is the integral of 1 by s? It is ln s with limit y0 to y, and then we have, what will be the integral of second term? This is also ln of a minus bs. We have the factor a, and we will also divide it with minus b, and the limit will be from y0 to y. Okay. So we can solve it further, and this term will be just, we can write ln y minus ln y naught, and using the log property, ln a minus ln b can be written as ln a by b. So using that, we have written ln y by y naught. And then this term, again, if you see, this minus 1 term can be absorbed in the logarithmic, and this will be ln 1 by 1 minus bs. And if we put the limits, we will get ln a minus by naught divided by a minus by. So is it clear to everyone?
Yes.
Now these logs are in addition. We can write multiplication, because ln a plus ln b is nothing but ln a into b. So this property we are using. So this will give us a minus, obviously the argument should be positive. So this is the integration of the left term. Now with this in hand, let's write the complete equation. So it is ln y by y naught a minus by naught a minus by, and this was equal to t minus t naught. Now can you find out the expression for y?
Yes, ma'am. This will be an exponential form of
Yes, exponential form. To proceed further, when you find out the solution, you will get to know why we are writing this. We have a minus by not greater than a minus by, or just we can have that this fractional term is positive, so we can ignore the modulus and we can write a minus by, and this 1 by a can go here. So when we solve it, we will have a form a y naught divided by by naught plus a minus by naught e to the power minus a t minus t naught. Okay, you can just remove this logarithmic by taking exponential of this and then solve for y. You will get this form of expression. So this is the solution y of t given the initial condition y naught at time t naught. So in the question, what is given to us? We are given that at t equals to 0, we have y equals to 1. Okay, before that, since we are deriving the solution for a uh, general ODE, which is nothing but the model of population growth, okay. So for this population growth model, we have this type of solution. Now when we will do the MATLAB session in the next week, I will show you how we can solve this type of ODE using MATLAB. So we will do, it is nothing, just we have to write this right hand side, solve using OD45 or these type of thing in MATLAB, and we can visualize how this y progresses with time, and in that also we can see how the solution of y or how the trajectory of y is varying with the parameter a and parameter y. Okay, now the beauty of this solution is that if you find out the limit t tends to infinity of this solution, what we will get? So we just have to put t tends to infinity. Then the numerator will be same. What will be the denominator? This by naught will remain as it is. This term, if you see this exponential, as t goes to infinity, will converge to 0, and this term will go to 0. So we will have just by naught plus 0. That means the limit as t goes to infinity is nothing but a by b. So what does it mean? The final value of the solution, is it depending on the initial condition? Does it depend on the solution as t goes to infinity? Does it depend on the value of initial condition?
No, ma'am.
No. Yes. So whatever the initial condition is, as t goes to infinity, the solution is going to converge to this value only. And this you can verify in MATLAB also. While simulating it, you can give different initial condition, but as you plot the trajectory for very last time, you will see that all those trajectories are converging to this value a by b. Okay, so this also revises your population model. Now using this solution, we have already identified what the limit is for such models. Now for this problem, can you identify the limit as t goes to infinity using the solution that we have just derived? So this data doesn't play any role in finding out the final limit. Okay, so a in our case is -5, b in our case is 2. Okay, so what is the limit? It came out to be a by b. So the limit a by b is -5 by 2. So any doubt, anyone? Okay, let's move to another problem. So suppose we have differential equation which is given as some function x, which is defined on t x x dash x double dash up and x triple dash, this equals to 0. So this is one set of differential equation where this function is an ODE with variables t x x dash x double dash x triple dash. Okay, then we have another differential equation t of y dash y double dash up to yn plus 3, this equals to 0. Find out the order of x and y and the domain of x and y. So what is the order of first differential equation? Where these dash represents the derivative. So x dash represents dx by dt, x double dash represents d2x by dt square,
3.
and so on. And similarly for y dash, y double dash. So the order of x is 3
3.
because the highest derivative is 3, so its order is 3. And what for y, capital Y?
N plus 3.
Yes, it is n plus 3. So order is nothing but the highest derivative that is present in the system. Now what are the domains of x and y? Whether it is r1, r2, r3, r4, rn. Now in order to identify the domain of ODE, we have to count the number of variables. How many variables we have in x?
It will be R4 and
R5.
How many variables we have in x? This one.
4.
No. How many variables?
2.
So
So
in all we have
5. R5.
t, x, x dash, x
Yeah, yeah.
double dash, and x triple dash. So in total we have 5 variables. So this x belongs to R5. Okay, because we are assuming all these are real numbers. If those were complex number, we would write is a subset of complex number. Okay, but we are assuming all these are real numbers, so it belongs to R5. Now similarly, can you identify for y?
Rn plus 5.
Okay, so how many derivatives we have? We have first derivative, second derivative up to n plus 3. So these are n plus 3 variables from first derivative to n plus 3 derivatives. Okay, apart from that we have this function y, variable y. Okay, this accounts for one another variable, and then we have t. Okay, so in total we have n plus 3 plus 1 plus 1. So it is r n plus 3 plus 1 plus 1, that is r of n plus 5. Okay, okay, now let's move on to our next problem. So we have to find whether this is an a linear differential equation or a non-linear differential equation. Okay, so the differential equation that is given to us is dy by dt equal plus t square y equals to et sine t. So this is number 1, and number 2 is dy by dt plus y equals to t.
Ma'am, can you repeat the question, ma'am?
We have to identify whether this ODE is linear or non-linear for each one, for the first one and for the second one.
First one is linear and second one is non-linear.
Okay. By which property we can say that these ODEs are linear and non-linear?
It's a if we take L means dependent variable is y, so L of y dash plus t square y, alpha y plus beta
Yes. So we have to
y dash.
basically,
So it is equal to what?
yes,
This
right.
linear operator type, linear transformation.
Yes, that's correct. So we anywhere, if we have to check whether any function or system is linear or not, we have to ensure that it follows the principle of superposition. Now how to implement that principle of superposition in this ODE, because we have to just check linearity with respect to dependent variables. So we form an operator which acts only on dependent variable. Okay, so for this one we can write it as y dot. By just looking at these equations, one can identify whether it is linear or non-linear, but for some functions which are some complex functions, it is not easy to just look and say whether it is linear or not. Okay, so in such cases we need to verify it using the linear operator formulation. So what we will do in that, we write our ODE in simple form like this, and then we have to take everything which is function of dependent variable. So this right hand term is independent variable, so we are ignoring it, and we find an operator L which acts on y, and in our case it is y dot plus t square y. Okay, and now we have to check whether this a1y1 plus a2y2 is equal to a1ly1 plus a2ly2. So this is nothing but the principle of superposition. So if it follows the principle of superposition, we say that this system is linear. Now if you check this property for this one, you will see that this comes exactly equal to the right hand side. So let's check that. So how to find L of a1y1 plus a2y2? So we have fixed our Ly. Now let's find a1y1 plus a2y2, and then t square of a1y1 plus a2y2. Okay, so this is the LHS of this one. Now let's find out a1 ly1 plus a2 ly2. What it will be? It will be a1 of y dot plus t square y1 and a2 of y2 dot plus t square y2. Okay, Now, can you confirm whether A and B are equal to each other?
Yes, ma'am.
So A and B comes exactly equal to each other, means this term is exactly equal to this term. So it follows the principle of superposition. So our this system or this ODE is linear. Now similarly we can check for second one. Let's form an operator. So L of y we can write as y dot plus y. Okay. And now again let's find a1 y1 plus a2 y2. What it will give? It will give us a1 y1 dot plus a2 y2 dot plus a1 y1, and what will be L of, sorry, what will be a1 L of y1? It will be y1 dot plus y1 and a2 of y2 dot plus y2. Okay. So here this A and this B, this is your B and this is your A. Are these equal to each other? So we have this a1 y1 dot, here we have also a1 y1 dot, a2 y2 dot, here also we have a2 y2 dot, but here we have mod of a1 y1 plus a2 y2, but here we have a1 mod of y1 plus a2 mod of y2. So we have a1 y1 plus a2 y2 not equal to a1 y1 plus a2 y2. Okay, since this is not equal, what we can conclude, that this ODE is non-linear. Is it clear?
Yes, ma'am.
Yes, ma'am.
Okay. Now let's move on to next problem. Okay. Now in order to brush up with the solution of first order differential equation, we are solving this question because these are used very extensively in all the future topics. So let's solve this question. So it is given, so we have to find the solution of initial value problem for dy by dx plus 3y equals to x, and it is given that y of 0 equals to 2. Okay, find the solution y of x for this initial value problem. Initial value of y at x equals to 0 is given to be 2. So if you all are able to solve these type of questions, you can easily solve the questions that are given in the week 1 assignment. So many of you who are from mathematics background must know what is the general solution for this type of ODEs. Suppose we have something dy by dx plus ay equals to bx. These type of ODEs, people from mathematics know very well how to solve these type of ODEs. Okay, so we make use of integrating factors for solving these type of first order differential equations. So what will be the integrating factor in this case? So again I will start with a general first order ODE, and using the solution of this general form we can find the solution of the one given in the question using the values of a and b. So for the problem given in question, we have a equals to 3 and b equals to 1. So we can put this in the solution, in the general solution, to find out the solution for our problem. Okay, so let's have a general solution for this type of ODEs. To solve that, we need to find out the integrating factor. So the integrating factor in this case we can find out, let's call it mu x. So this is a here, so this is nothing but integration of a dx, so it will be e to the power ax, because here a is a constant. Now we have to multiply both RHS and LHS with this term, so e to the power ax into dy by dx plus a into e to the power ax into y equals to bx e to the power ax. Now anyone can identify which function derivative uh, this represents?
D of y e to the power ax.
Yes, we can easily write it as derivative of, or we can write y into e to the power ax. Okay, so when we find its derivative, it clearly gives us this term, and this is nothing but equal to e to the power ax. All right. Now this we can write as integration of px ex. Okay, and what will be the integration of this? You can find out using integration by parts. So it will give you bx e to the power ax by a minus b by a square e to the power ax plus obviously an integration constant, and this is your y e to the power ax. Now integration by parts, I assume you all know. So in integration by parts we do we left, so I am using this as first function and this as second function, because exponentially we generally use at the second part, and so we left the first part as it is, then we integrate the second part, and then we use minus of differentiation of first part, so it gives us b, then integration of second part, and then again the integration of that whole second part that is there. So this will give you this term. Now with this we can easily find out y by dividing with e to the power ax, so it will give you b by ax minus b by a square plus c e to the power minus x. So this is the general solution for this first order ODEs. Now the question is asking about the solution for this initial condition. So you can use the data of this initial condition, that is at x equals to 0, y is equal to 2, to find out the value of c. Can you please find out what is c? Using the fact that at y equals to 0, at x equals to 0, we have y equals to 2. You can also put the value of a and b. So we have a equals to 3 for our case and b equals to 1. Anyone has solved for C?
Is it 2, ma'am?
2. Okay, I haven't solved it, so let's see what it comes out. For B we have 1, A we have 3, okay, and x equals to 0, and then 1 by 9 plus, now if x equals to 0, this exponential will be 1, so we have C, and now this is equal to 2. Okay, so C is equal to 2 plus 1 by 9. It is 19 by 9. Yeah, so C is approximately equals to 2. So what we need to keep in mind is the general solution of first order ODEs, which is given using. So we have a proportional term, a constant term, and an exponential term. You can remember it like this. A proportional, a constant, and an exponential. Okay, let's move on to another problem. Okay, so we have a simple question where we have y double dot plus 4y equals to 0. We have to represent it using set of first order differential equations. What is the order of this ODE? The
2.
order, the order of
2,
this ODE is 2. So how many first order ODEs we need to represent this equation, this differential equation? The order is 2, so we need 2 sets of first order DEs to represent this particular differential equation. Now how can we choose the variables? So how can we convert this second order DE into first order DEs, into set of first order DEs? To do so, we set the variables. So what we do, we take a variable x1 and say that this x1 equals to y. Then we set another variable x2, which is y dot. Okay, so we have two variables, y, which we have assigned it as x1, and then y dot, which we have assigned as x2. Now let's find out x1 dot, that is dx1 by dt. Okay, this will be nothing but y dot. And what is y dot in our case? It is equal to x2. So this gives us what? x1 dot equals to x2. Now let's find out the derivative of x2. x2 dot is y dot. Okay, so x2 dot will be y double dot. And what is y double dot? It is equal to, using this we can find out, y double dot is minus 4y. Okay, and what is y? Y is x1 in our case, so we can write x2 dot equals to minus 4x1. So is this transformation clear to everyone? And how we have uh, found out x1 dot and x2 dot? Now in this set of first order differential equation that we have just derived, which is x1 dot is x2 and x2 dot is minus 4x1, what change of variables we have performed? So we have transformed y with x1 and y dot as x2, and using this change of variables we have find out the first order differential equations, that represents the same differential equation which was of order 2. Now we have represented the same differential equation using first order differential equations. And in matrix form, how can we write it? So we have x1 dot, x2 dot. We have to find out this matrix x1 and x2. So what will be the size of this matrix? This matrix, okay, so let's first write, then we will identify the size of this matrix. So x1 dot is x2. How can we extract x1 dot using this matrix formulation? The entry should be 0 and 1. Is it correct? So this will give us x1 dot equals to x2. Now what about x2 dot?
Minus 4
minus
and 0.
Minus 4 and 0. Okay, so this is the matrix A. So in short we can write x dot equals to Ax, where A is this matrix and x represents the vector x1 x2. Okay, so this is how any differential equation can be represented using a set of first order differential equations. And this is what this is the core of control systems, because if you see the linear systems theory, you will see that always we represent system using the form x dot equals to Ax. Okay, so x dot equals to Ax requires us to transform differential equation into a set of first order differential equations. Now in this case our A is a constant matrix. It is 0, 1, minus 4, 0. But in some cases, it can be a time varying matrix also. And in some another cases, we have some extra term over here also. We call that as forcing term. So that system is called as forced differential equation. Okay, or we call it as non-homogeneous differential equation also. So in this way, we will first model our system using differential equation, then we will transform it using ODE, and then we get a beautiful form of differential equation in the matrix formulation. Okay. Okay, so similar to that, we have this problem. Okay, where we have y double dot plus 4y dot minus y equals to 0, and you have to choose variables as x1 equals to y plus y dot and x2 equals to y dot. Find the matrix A, that in x dot equals to ax formalism, find out the matrix A if we have performed this transformation. Question is clear to everyone? And also please let me know if I do any mistake anywhere. Okay, so the change of variables that we have to do is x1 is y plus y dot and x2 is y dot. Okay, so with this change of variables, we have to find out x1 dot and x2 dot, then only we can find out the matrix A. So for x1 dot, we have y dot plus y double dot using this first equation. Now this y dot is nothing but x2, so we can directly write y dot is x2. Now what is y double dot? This y double dot is minus 4y dot plus y. Okay, but we have to write in terms of x1 and x2 only. So this y dot again we can write as x2, so this is minus 4x2. And what about y? Y we can write from here, so y is x1 minus y dot or x1 minus x2, because y dot is x2, so it is x1 minus x2. So these x2 will cancel out, and then we have x1 minus 4x2. Similarly, what will be what will be x2 dot? X2 dot will be y double dot, and y double dot is minus 4y dot plus y, and y dot is x2, and y is, here we have find out y is x1 minus x2, so it is x1 minus 5x2. Now can you find out the matrix A? Let me write. We have x1 dot is x1 minus 4x2 and x2 dot as x1 minus 5x2. What will be A? So it will be very easy, 1 minus 4 and 1 minus 5. So we have one system which is represented using the differential equation y dot equals to square root of y with initial condition y 0 as 0, and another system which is represented using y dot equals to y cube, and again the initial value is 0 at 0. You have to identify whether the solution will exist, and if it exists, whether it will be unique or not for each of these systems. So the first one, the solution will exist or not for the first ODE. Now in order to check the existence of solution, we have to check whether this RHS is continuous or not. So square root of y is continuous or not? The square root of y is continuous. Okay, anyone having any doubt in this? Okay, and for uniqueness, what it should satisfy, the right hand side? The right hand side should be Lipschitz. Okay, so in order to verify that, we can find out whether the partial derivative of f, which is this right hand side, we call it as f, whether this f is bounded or not, that the bound is m. So if it satisfies this, then we can confirm that the solution will exist and it will be unique. Existence is coming from the continuity, and uniqueness will come from the Lipschitz property, or we can also uh, confirm it using whether the partial derivative is bounded or not. Now can you find out the derivative of partial derivative of this f with respect to y? So the partial derivative will convert to derivative only because there is no term of t over here. So we have to find df by dy. What it will be?
1 by 2 root y.
1 by 2 root y. So whether this will be bounded or not, for example, let's suppose I am talking about some rectangle where t is from 0 to t capital T, and this y is from 0 to, let's say, some value, or minus b to b I'm talking about. So in this rectangle, if I talk about whether this derivative will be bounded or not.
At y equals to 0, the boundedness fails, I think.
Yes. So everywhere else, if y is not equal to 0, this partial derivative or derivative is defined for all y and it remains bounded. But as y tends to 0 or y equals to 0, this term will go to infinity because we have y the denominator. So it is ill-defined in the neighborhood of y equals to 0. Okay, and we are talking about the rectangle minus b to b. So it doesn't satisfy the property of Lipschitzness. So we cannot say that there will be a unique solution for this differential equation. Okay, now what about the second one?
And the second one is a simple polynomial function.
Yeah.
So it is continuous everywhere.
Yes.
And also, since there is what I say, no undefined in any rectangle, we cannot find any undefined
Yes.
part. So it will be Lipschitz also everywhere
Yes. Yes.
in a local rectangle or like local area.
Yes.
If we say that.
Thank you. So existence is coming from the continuity of yq. So it is a polynomial function. So it is continuous. So the solution will exist and uniqueness is coming from. So if you find out df by dy, in this case it gives you 3y square. Okay, so since we have a square term, it is just 3y square. Now when you define any rectangle, then in that rectangle this partial derivative is defined for every y, and also in the rectangle we can also find out its bound. So its bound will be, if we have defined y less than equal to b, its bound will be 3b square. Okay, so we can conclude that the solution for this differential equation will exist and that solution will be unique as well. Okay. Okay, one last problem for this session. So we have a system which is represented as x dot as matrix 0, 2, minus 2 and 0. Now the first part is represent it as second order differential equation. So we have to go the other way. So earlier we have transform second order ODE to first order differential equation. Now we have to go the other way. We have to convert this first order set of first order differential equations to second order differential equation, and then we have to check whether, so we have to basically find out the set of solution, or we can say solution for y dash. Okay, and we have options as cos 2x 2 sin 2x. Second we have cos 2x minus 2 sin 2x, and third we can take as cos x sin 2x. Or we can take, sorry, t, because that may confuse you. Okay, so we have a differential equation first represented using a second order differential equation. Now with that, so the variable will be y. With that differential equation, you have to find out what can be the possible solution for y and y dash. So the first option is cos 2t 2 sin 2t, second is cos 2t minus 2 sin 2t, and third is cos t sin 2t. Okay, so if we expand this matrix formulation, we can get x1 dot equals to 2x2, and x2 dot we can get as minus 2x1. So what will be the double derivative of x1? Let's find out x1 double dot. So it will be 2 x2 dot, and x2 dot is nothing but minus 2x1. So it is 2 minus 2x1. So it will be minus 4x1. Okay, so we can write this as x1 double dot plus 4x1 equals to 0. Now we can take x1 equals to y. So this is nothing but y double dot plus 4y equals to 0. Okay. Now what is the solution of such differential equation? So we have transformed first order ODEs to second order differential equation with variable y. Now what is the general solution of such differential equation? So we have second order ODE. So this is nothing but the equation of model of oscillator. Okay, we have second order derivative of y double dot plus 4y equals to 0. This is nothing but an oscillator dynamics, and we know the oscillator has the solution as sinusoids. So we can write, and we have the natural frequency as 4. So the solution is given as You can also verify that using by transforming it into polar coordinates, then finding out the eigenvalue, and then you can find out its solution. And this solution is nothing but cos of, so if we have y double dot plus a y equals to 0, the general form, the solution is given as c1 cos under root at plus c2 sine under root at. Okay. Now in our case, a is 4, so yt is c1 cos 2t plus c2 sine 2t. Okay. But which option among these is correct? We have to identify the possible solutions for y and y dash. Which option can be true? So we suppose that because we have to identify one possible solution, so we assume that this c2 is 0 and c1 is 1, then my y of t will be cos 2t, and in that case y dash t will be minus 2 sine 2t. Okay, so is there any option like this? So the first option is not like this. The second option is cos 2t minus 2 sine 2t. Okay, so in this way we can identify possible solutions for a given differential equation. And I think we are done for today. We have some more problems. Okay. Okay, for the next session, what I want is please go through the solution for a general second order differential equation y double dot plus py dot plus qy equals to 0. So if we have this type of second order differential equation, what is the solution y of t? The general solution y of t. Okay, and you can also find out for y double dot plus qy that we have already seen over here, the general solution for this type of ODEs. Okay, because in this way if we have any model that because these are one of the general models that we will come across in second order differential equations, and if we have the solution of them in our mind, we can easily solve for final value problems or uh, the effect of parameters which are over here p and q, and whether what is the role of initial condition for such differential equations, how will the solution change by varying these p and q, because we will see that for this type of second order differential equation, by changing the value of p and q drastically changes the solution. Sometimes it can be exponential, sometimes it can be sinusoidal, like that, or it can be even linear also. So uh, if I will try to give you a brief explanation on how to find out the solution for these two types of differential equations, and then you can also solve many problems related to that, and you can also simulate that in MATLAB also. So that's all for today from my side, and if you have any suggestion or you have any question, you can ask.
Ma'am, I have one question.
Okay.
Ma'am, for the 75 marks, we have to go through the CBT test, no? So, is that in the form of MCQ or in like?
The questions will be based on MCQs only.
Okay. So, as we get the gate exam or like that, no? CBT.
Mm-hmm. Yes.
Yeah. Okay.
Like
So
that.
all are MCQ, no?
Yeah, all will be like MCQs. So the
Ah.
type of questions that you have in the assignments,
Mhm.
only that type of questions will be there, and those type of options you will have there.
Okay. Sure. Thank you very much, ma'am.
Thank you. Okay, anyone? Any question or suggestion? Should we keep these type of numericals in the session?
Ma'am, I have one more question.
Mm-hmm.
Yeah. So for the assignment for week 0,
Yes.
the marks for assignment week 0 is calculated for the final.
No. Only the week assignments will be calculated
Okay. From week 1 and
from
onwards.
week
All.
1.
Yeah.
From week 1 to week 12.
Okay. Yeah. Thank you.
Week 0 is just for your
Practice. Okay.
practice, yes.
Yeah. Okay. Thank you, ma'am.
So have you all solved the assignment problems?
No,
Week 1
ma'am, left out.
assignment? Okay.
No, ma'am. Some of are left.
Okay. I think after this, you all will be able to solve the assignment problems. And some problems that are model specific. If you see the assignment problems, some are very model specific problems. So that you can revisit the recorded lectures and you can easily see the solution is directly given in the videos only. And other problems, I think with this session and the recorded lectures, you all will be able to solve the questions. Okay, then let's meet next week, and from next week I will try to first make you revise what all the contents have been covered, and then few problems on MATLAB, and these type of questions we will also have in the next week. Okay.
Ma'am, I have a doubt. With this session, whatever we discussed so far, can it be revisited or is it recorded? Any option is there?
Yes, these notes and also this live session recording will be uploaded in the, I think there is one sheet you will be shared, and I think
Oh,
it is already shared with you. You can access that
okay, ma'am.
whenever you want, because
Fine, ma'am. Thank you.
the
Yeah.
recording of this is uploaded to YouTube, so you can revisit it anytime.
Okay, ma'am. Thank you.
Okay, then thank you all. Thank you so much for joining this course and for joining this tutorial session. Thank you.
Thank you all. Thank you.
Thank you, ma'am.
Thank you, ma'am.